Good evening, students. Welcome to the finite element method CE3206 course. In earlier lecture, we had discussed about the derivation of the Gauss point quadrature for 2 points. Then we use the numerical Gauss point quadrature example. We solve one example where on this domain so we can have this point as u2, this point as u3, u2 and u1 bar. Okay. And to connect it, we can use a linear element. So, we will connect it by a linear element here, linear shape function. So, we write the global trial solution in this form: u h of x is u, this is u h of u1 times, let us call I think we have to introduce the shape functions also. So, let me introduce the shape function here. I think 1, 2, 3. So, the global shape functions are like this. So, the value at the nodes is 1. So, this is shape function 1, it has a value of 1 at node 1 and remaining at node 2 it has a value of 0, and intermediate points we have n1, it is a linear function. And for node 2 its value is 1 at shape function 2, its value is 1 at node 2 and remaining points it varies like this. So, this is n2 of x, and shape function 3 at node 3 it is 1 and at remaining at node 2 it is 0, and in between it is connected by a linear. So, this is n3 of x. So, we can write the trial solution as u1 n1 of x. Actually, it is u1 bar because this value is known, we are fixing it, and then we have u2 n2 of x plus u3 n3 of x. So, in this problem u1 bar is known and u2 and u3 are unknown, these two are unknown. Okay. So, the trial solutions in this problem we have we are choosing this, we have to find this unknown u2 and u3. Okay. And weighing function, what we did, we had the weighing function written like this. We will denote it E times u e. Okay. And du by dx, I will write it as ne times so dne by dx times ue, which is be times ue. Okay. Okay. Now, let us go ahead and substitute in the weak form. Let us do it. Let us substitute in this. Let us evaluate that integral. Okay. Before doing that, yeah, let us do it. X1. Okay. So, the first term dw by dx. Okay. So, this term we will write it as W E transpose B, and this term we will write it as B E times U E, and we have our E A term which is dropping, which remains the same, and then our dx. Okay. So, in this integral u e is the nodal value. Okay. u e term is the nodal value and w term is also a nodal value. Interior b x term is a function of x, b is a function of x and b also is a function of x. So, we can take out w transpose out and u e also out of the integral. Okay. So, what we will do now, we are taking the w transpose out, and then we are having this integral x 1 e to x 2 e b transpose E A B E, and then we are taking the u e term also out, times dx, and then we are taking the u e term also out. Okay. So, we denote this term, this entire integral, we denote it by K E. Okay. It is the element stiffness matrix, and the remaining terms will be same W transpose, and here we have the U E. Okay. So, this K E matrix let us evaluate and see what we get. K E is called the element stiffness matrix. We had derived the element stiffness matrix for a 2 node axially loaded element in the first few classes. It was E A by L 1 minus 1 minus 1 1. We derived it directly. Here we use this FEM approach and derive the same thing. For linear node, it will be almost, it will match exactly. If you want more accuracy, we can have a suppose a 3 node element, then it is not possible to derive manually, like the directly we cannot derive, we have to use this FEM approach. We have to evaluate this integral. So, anyway, for this linear approximation, let us derive it. Okay. So, what is B E transpose? Can you look at here and tell me what is B E transpose? B E transpose is d n E by dx, d n 2 by dx, right. So, let us write the term d n 1 E by dx, d n 2 E by dx. So, this is our B, and then we have our E A term. So, the shape function for a linear shape function is like this. This is n 1 of x between x 1 e to x 2 e. So, n 1 e of x is x 2 e minus x 2 e minus x by x 2 e minus x1e, okay, and dn1e by dx, it will be minus 1 by x2e minus x1e, which is minus 1 by LE. Similarly, for the second shape function n2, so here x2e and x1e, it will be x1e, sorry, it will be x minus x1e by x2e minus x1e. Okay. So, dn2e by dx, it will be 1 by LE. Okay. So, let us evaluate the integral ke. I think we will do it in the next slide. So, ke will be minus 1 by LE times 1 by LE. Okay. So, let us do that. Previous slide. Yeah, maybe I will write it here. Ke is integral x1e to x2e minus 1 by LE, 1 by LE, then EA 1 by LE minus 1 by LE and 1 by LE times dx. So, 1 by LE square minus 1 by LE square, sorry, and the next row will be minus 1 by LE square, 1 by LE square. So, we can take it out of the integral, and EA also we can take it out of the integral. We will be left with integral dx from x1e to x2e. So, effectively what you will get, dx will be x2e minus x1e, which is LE. So, finally, we get our ke value as I will after copy I will go to the next slide. This term will be LE. Okay. So, yeah. So, I will go to the next slide, and we will write the element stiffness matrix Ke as EA by LE, and we have 1 minus 1 minus 1 plus 1. Okay. So, we have taken 1 by LE common, 1 by LE square common, and then LE by 1 by LE square will be 1 by LE. So, we get our element stiffness matrix. So, this was the same matrix which we obtained by directly. Okay. So, if you look at the first term of the, if you do that, before going there, let us come back to this equation. So, what we are doing here is, yeah, we are having this integral x1e to x2e, sorry, let us look at this term carefully. Okay. Let us look at this term and this term one more time. okay, W transpose Ke UE. Okay. So, the first term was W1 and WE1 and WE2. Okay. So, the first term is WE1 WE2. So, let us write it down, WE1 WE2, and then the Ke term is EA by LE 1 minus 1 minus 1 1, and the UE term is UE1 UE2. Okay. Okay. Now, we will do a summation. Let us do the summation for that element. Okay. It is like it is better to do it and see what happens. So, we had our nodal values U1, which is U1 bar, and then U2 and then U3. So, what is UE for? Let us write U for element 1. So, for element 1 it will be this node and this node displacement at this node and this. So, it will be U3 U2 in terms of global nodes. Okay. And WE we will write as W1. So, that also we will have to write, we will write that here 1, 2 and 3. Here W1 is 0, then you have W2 and W3, which are arbitrary values. Okay. So, this is element 1 and this is element 2. So, W1 will be W3 and W2. Okay. Similarly, for the first W, let us look at U2. U2 for the second element will be U2 and U1. Okay, U2 and U1. And similarly, W2, weighting function 2 will be W2 and W1. Okay. Now, let us evaluate W transpose Ke UE individually and see what happens. So, here our term, first term will be W3 W2, second term is EA by L1 1 minus 1 minus 1 plus 1, and U1 will be U3 U2. Okay. And this other term W2 transpose K2 U2. So, that we write as W2 transpose W2 W1 EA by L2 1 minus 1 minus 1 1 u2 u1. Okay. So, if you want to sum up these two equations, we want to establish our global coordinates and then do the summation. So, to establish our to relate these matrix with the global displacement matrix. So, this is the sorry, we want to relate this matrix with the global displacement matrix, also this matrix with the global displacement matrix, this matrix with the global weighing function values at the nodes, and this matrix with the global weighing function values at the nodes. So, what I will do is I will relate that using the scatter matrices. Okay. So, we have our u1 which is u3 u2, and then I will introduce the scatter matrix L1 times u1 u2 u3. Okay. So, if what will be the scatter matrix? This is a I want a 2 by 1 row 2 by 1 matrix, and this is a 3 by 1 matrix. So, this will be 2 by 3. Okay. So, I will have a 2 by 3 matrix here, and the values will be u3 is there. So, first two terms are 0 and next term is 1. Next term is u2. So, first u1 term coefficient is 0, u2 is 1 and u3 is 0. So, this will be our L1. So, this is our L1. Okay. Similarly, for D the other matrix is there W3, we will do the similar exercise. W1 is there which is W3 W2. So, we will get a similar term here 0 0 1 0 1 0 and then W1 W2 W3. So, same scatter matrix is there, and W1 transpose will be W one it will be the transpose of this. So, it will be W1 W2 W3 times transpose of that, which will be 0 0 1 0 1 0. Okay. So, this is actually W transpose, the global W transpose. Let us denote by some name. So, let us call this D vector, and what we will call this? Let us call this as maybe let us say dW vector, okay, and this will be L1 transpose. Okay. So, effectively what is happening is we are writing W1 transpose K1 times U1 as dW transpose, that is global weight vector transpose L1 transpose KE L1 and the global vector. The same exercise we can repeat for the other second element. So, W2 transpose K2 U2 we will write as global shape vector transpose global weight vector transpose L2 transpose K2 L2 D. So, as an exercise let's see what will be our L2 for L2 value. So, we have U2 here, U2 will be, what is U2? It is U2 times U2 and U1. So, we have to fill up a matrix like this, and we have U1, U2, U3 here. So, coefficient of 1 is 0, coefficient of u2 is 1, coefficient of u3 is 0, and coefficient of in the next row coefficient of u1 is 1, u2 is 0, u3 is 0. So, this will be our LE2. This is our L2 and this is our global displacement vector D. Okay. Is this clear, this part? The scatter matrices I have introduced, and why I am introducing it? So that what I will do is I will take out these terms, this term and this term. I can add them because D are common here, dW and dW are common there. Okay. So, when you do the summation, when you add this term and this term, dW terms I can take it out, and L1 KE L1, L2 K2 L2 I can add it up. Okay. So, that is the reason I am introducing the scatter operation here. Okay. So, if you look at these two terms, this term and this term, obviously these terms are W2 and W3, W2, W1. It's difficult to add it up. So, I have created a scatter matrix and made sure that the first multiplying term and the last multiplying term are same, and the intermediate terms we can add it up. Okay. So, that is the reason I have introduced the scatter matrices. So, effectively the integral will become sigma E is equal to 1 to number of elements, the summation of x1e to x2e this will become summation E is equal to 1 to number of elements. So, the first will be the dW term, global weight terms. Next term will be L E transpose times K E times L E, and then we have the global displacement vector for the trial solution. Okay. So, we can take out this term and this term out. So, I am taking them out here. So, I will get dW transpose and D on the other side, and the summation now will be between E is equal to 1 to number of elements, L E transpose K E L E. Okay. So, this term is called the global stiffness matrix. Global stiffness matrix, we can denote it by capital K. Okay. So, to summarize, what we have started is, we have started with the first integral dW by dx A du by dx, then we summed up over each element. So, integral sigma E is equal to 1 to number of elements, dWe by dx times Ea du by dx. Okay. So, we had taken a 2 node element, and then local node numbers are 1 and 2, x1e and x2e are the local coordinates. So, we are evaluating this integral dW by dx Ea du by dx. So, we have WE term, which is a trial weighing function term. So, I am having n1, which is a function of x times W1e plus n2e of x times W2e. I can write it like this, or I can write it like this. So, I am writing it like a W transpose times NE transpose. Similarly, dW by dx I will write it as W1e times WTE and dN1e by dx, dN2e by dx, and this term I am calling it as B transpose. And shape function using the trial solution for the element level, at that element node 1 we have u1e, and at node 2 we have u2e. So, I am writing u as n1e u1e plus n2e u2e. I can write in matrix as any times ue, and du by dx I am writing as bue. Okay. So, now I substitute du by dx and dw by dx into this here and here. So, I am getting w transpose b here and w transpose ue. I will take out w transpose out, ue out, and from the integral, because they are nodal values and they are not dependent on x, and this term we call it as ke, okay, which is a b transpose EAB, and it is called the element stiffness matrix. So, we will evaluate the element stiffness matrix by taking the by doing the integral. So, the shape function is given, n1e of x is given here, and n2e of x is given. If you do the derivative with respect to x, we get minus 1 by LE, and dn2 by dx you will get plus 1 by LE. So, if you substitute it, we get the element stiffness matrix, which is EA by LE 1 minus 1 minus 1 1, which was similar to what we had done in the earlier direct approach. Now, we want to evaluate the summation. So, if you look at the summation terms W1 transpose K1 U1, it has W3 W2 and U3 U2, and W2 transpose K2 U2, it has W2 W1 and U2 U1. We cannot add them up directly. So, I am doing a scatter operation. So, I will relate these U1 terms, which is U3 U2, with the global displacement vector D, okay, by using the scatter matrix L1. And similarly, for W2 also I will do the for the weights also I will do it. So, the same function will be there, L1 will get. If you take the transpose, you will get dW transpose times L1 transpose, and if you substitute it, you get dW transpose L1 KE L1 times D. Similarly, for element 2 we have dW transpose L2 K2 L2D. Okay. So, we can dW and D terms are taken out, and we get the summation like this. Okay. So, this LE transpose KE LE summed up over the all the elements is called the global stiffness matrix K. Okay. So, in today's class we have learnt about the element stiffness matrix and the global stiffness matrix formulas, and we will go into the details in the next class. We will go into the, look into the other terms, so WB dx and WA T bar in the next class. Okay. So, this WB dx will be the global force vector, including the traction term. So, both we will look into it in the next class. Okay. So, thank you for your attention. Element force matrix by dx A du by dx minus integral 0 to L WB dx minus WA T bar at x is equal to 0. This is satisfied for any W of x with W of 0 is 0. So, we looked at the first term of this expression, and we saw that we can write it in this form as summation over each element, and we have introduced the global stiffness matrix in the earlier class. So, our first term of the weak first term in the weak form, we are writing it as a multiplication of 3 terms. One is the weight terms, second one is the global stiffness matrix, and third one is the unknown displacement values. So, this in this equation W1 W2 are arbitrary. Okay. These are arbitrary, and this arbitrariness will help in help us to get the linear algebraic equations in stress analysis. Those are the stiffness equations. Okay. So, let us calculate K global for this specific problem and see what value we get. So, we have this 2 node element, and for this 2 node element we have, let us find out K1 matrix. So, K1 matrix we can write it as EA by L1, and it is 1 minus 1 minus 1 plus 1. And now our U1 vector, it will be the displacement at node local node number 1, which will be in this case U3 and U2. So, this we can write it as scatter matrix times the global displacement vector. So, U1, U2, U3. So, in the first row the coefficient of U3 is 1 and remaining coefficients are 0. So, we can write 0, 0, 1. Second row the coefficient of U2 is 1 and remaining are 0. So, we write as 0, 1, 0. So, this is our L1 matrix. So, let us calculate this term L1 transpose times K1 times L1. Let us do the calculation. So, here L1 transpose is 0, 0, 1 and 0, 1, 0, and K1 is EA by L1, and then 1 minus 1 minus 1 1, and then L1 is 0, 0, 1, 0, 1, 0. So, if you do the multiplication of these two terms, we get 1 and minus 1. So, we will get 0, and 1 into 0 minus 1 into 1 minus 1, 1 into 1 1. Second row minus 1 into 0 and both terms are 0, and minus 1, and we will get plus 1 and minus 1. So, again we will multiply with 0 1, 0 0 0 1 1 0, and our EA by L1 is there. So, we go ahead with the multiplication again. So, we get 0, next term is also 0, and the other third term is also 0. Second row we get 0 and plus 1 and minus 1, and this one is 0, this one minus 1 and plus 1. So, this is our first matrix. This is the L1 K1 L1 term. Now, let us look at L2 K2 term, L2 K2 L2 term. So, for that we have to look at the second element, which has nodes U2 and U1. So, let us sketch it one more time. So, we have the second element displacement vector as U2 and U1. So, this we will write it in terms of the scatter matrix as U1, U2, U3, and we have coefficient of 1 for U2. So, remaining are 0, and second row coefficient of 1 for U1 and remaining are 0. So, this is our L2 matrix. Okay. So, let us calculate L2 transpose K2 L2. So, this will be 0 1 0 1 0 0, and K2 will be EA by L2, 1 minus 1 minus 1 1, and L2 is again 0 1 0 1 0 0. So, let us do the multiplication of the first two second two terms like we did in earlier case. So, this will be minus 1, and next will be plus 1, and next term is 0, and this term is 1, and next term is minus 1, and remaining term is 0, and we have our EA by L2 term. So, if you do the calculation again, we will get 1, the next term will be minus 1, 0, minus 1, 1, 0, 0, 0, 0. So, we can sum up these two terms. We can sum up this LE, KE and LE terms. So, we will sum up this and this. So, let us denote this term by K1 or let us denote it by K1, I think it is fine. We will denote this entire term by K1. So, we will get, and then this term by K2. So, if you do the summation, sigma is equal to 1 to 2 LE transpose KE LE. So, it will be a summation of two matrices. The first matrix is 0 0 0 K K2 K1 like this. So, 0 0 0 0 0 K1 minus K1 minus K1 K1, and second matrix will be K2 minus K2 0 minus K2 K2 0 0 0 0. So, if you sum it up, we will get K2 minus K2 0 minus K2 K1 plus K2 minus K1 0 minus K1 plus K1. So, this is our stiffness matrix, and the first term or the integral 0 to L dw by dx EA du by dx will become it will be like this: W1, W2, W3, and then the stiffness matrix K2 minus K2 0 and then the displacement vector U1, U2, U3. Okay. So, these are arbitrary values, and we will work with them in the when we evaluate the next expression also. We will write the expressions like this. We will have this arbitrary values. So, that dw transpose, and then there will be a matrix. So, we can take the dw transpose term out, and then we will get one stiffness set of stiffness matrices, stiffness equations. Okay. So, first term we are done completely, and now let us look at the second term, integral 0 to L WB dx. So, here so again W is the weighing function, B is the body force vector, is the body force function. So, B of x is body force. So, we can have a constant body force, or we can have a body force which can vary linearly. Suppose for this problem we can have a B of x is equal to B. So, it will be constant throughout, or we can have something like a linear variation. So, it might we can get some values like this. So at node 1 it is B1, here it is B2 and it is B3. So there is a linear variation between nodes 1, 2 and 3. So we can have a body force vector like this also. So either way it is, I think the first case is like this, all three are constant terms equal to B, and second case it is a linear variation. Okay. If we have linear variation, it will be we will look at the linear variation and see what we will get. So for linear variation, we can write B of x as in terms of shape functions. Okay. So what we will do is, we will split up this integral as summation over each element e is equal to 1 to number of elements, and then the integral will be x1 e to x2 e, and then we have w e of x, and then we have b of x in the element times dx. Okay. So earlier we have discussed about the w e of x, how we approximate that weighing function. I think we can write it as like this. We can write it as w e1, w e2, and then the shape function n1 e of x and n2 e of x. So this term we will call it as w the vector transpose, and this will be the shape function vector transpose. So we had done it in earlier class for the first integral. So we will repeat the same thing here. And then b of x, what we will do is, since you are assuming a linear shape function, linear variation in the element, what we will do is, we can write it as b1 of n1 of x plus b2 of n2 e of x. So what it means is that at node 1 and node 2, so at node 1 we have a value of b1 e, and at node 2 we have a value of b2 e, and in the intermediate space it is a straight line. Okay. So this is our b of x. Okay. This is our b of x. So we can write, I think actually we can maybe put like this, b of x. Yeah. So the integral x1 e to x2 e, that we will go ahead and write. So we will write it as w1 e, w2 e, this we take it out, and then x1 e to x2 e, then we have n1 e of x, n2 e of x, and then b of x we write as, we can write it as n1 e of x, n2 e of x, and then b1 e, b2 e. So, the same thing I am writing it here, n1 e of x n2 e of x times b1 e b2 e. So, now we will have a times dx. Now, we can evaluate this integral, this entire integral we can evaluate. Okay. And it will be a 2 by 2 matrix, this will be a 2 by 2 matrix, and I am not doing the integral calculation, I will just write the terms and then I will write the final values, okay, because it will take some time for do it manually in the class. So, I will just give the idea and you can work out the details later at home. Sorry. So, if you do the first integral, it will be integral n1 is whole square x dx. So, it is actually integral x minus xe2 by le whole square dx integral from x1e to x2e. So, we write it as x minus xe2 whole cube by 3. So, you will get first term as 0, next term is minus of minus, it will be plus. So, I think you will get minus of whole cube by 3 le square. So, this we will get as le by 3. Similarly, the other integral, this integral also will be integral x1e to x2e n2 of x whole square dx we get as le by 3. And then the and then n1e n2x integral we can evaluate in the next slide. So, it will be x minus x2e by le, and it will be x2e minus x by le times dx. So, if you check at x1e you will get sorry, I think at x1e you should get minus 1. So, yeah, it will be minus here, and here at x2 it will be this. Okay. So, if you do the integral calculation and all, you will get I think first integral will be a whole square by minus le times x2e minus x by le, and it is evaluated at x1e and x2e. So, I am doing integration by parts. So, I am integrating the first term and keeping the second term constant. without not changing the second term, and then what I will do, I will differentiate. So, I will again have this term x minus x 2 e whole square by minus L e, and then I am differentiating the second term, it should be minus 1 by L e times d x. So, what I will get is this term will go to 0, this term will be 0, and let us look at what happens to the other term. So, this term will be x minus x e, okay, we will have minus minus plus. So, there will be another minus there. So, x minus x e 2 whole cube by 3 L e square, and then the limits will be x 1 e to x 2 e. So, I have missed one 2 term here. So, the 2 term will be there. Okay. So, if you substitute x 2 e, you will get 0, and then if you substitute x 1 e, you will get minus L e cube. So, effectively we will get minus plus L e by 6. It is L e by 3, L e by 6, L e by 6, L e by 3, and then B 1 e, B 2 e are there. So, the effectively the integral W e x B of x dx, what you are getting is, we are getting W 1 e W 2 e and then we are getting the matrix L e by 3, L e by 6, L e by 6, L e by 3, and then B 1 e, B 2 e. So, this entire vector is usually denoted by one simple term. It is the element body force vector. So, we write it by this notation. Okay. It is the element body force vector. Okay. So, if you look in terms of integral, this term and this term will be our element body force vector. Okay. Okay. Now, we can do one more transformation. What we will do is, this vector we will convert into the global weights. So, what we will get is, we will write it in terms of global weights. So, yeah, we might do it later. I think I will illustrate it with the example, so that it will be more clear. So, what I will effectively do is, I will convert this W matrix into the global weights matrix times L e transpose. Okay. I will do this transformation. So, that what I will effectively get is, I will get d W transpose out, and then we have L e transpose, and then the element body force vector. And when you do the summation from sigma E is equal to 1 to number of elements. So, we will have x 1 e to x 2 e, W and B e dx. This summation, what will happen is, this term will come out, and we will be left with omega. Okay. So, we will get the global force body force vector. Okay. This term whatever we are getting, this will be the global body force vector. So, it looks a little theoretical. So, let us do the implementation for the 2 node element and see how to carry out this process. Okay. So, we will first start with this thing, we will start with this first scatter operation, and then for the first element, and then we will go to the second element and then do the similar scatter operation. Okay. So, for the element 1, sorry. So, for element 1 we have W1E and W2E. So, that is actually W3 and W. So, that will be W3 and W2 and W1. Okay. So, that will be there, and yeah. So, this is element 1. So, for element 1 the matrix will be W3, W2, and then the next one next term will be LE by 3. So, it will be L2 sorry L1 by 3, L1 by 6, L1 by 3, L1 by 6 and L1 by 3. And here B1E and B2E for element 1 is actually corresponds to node 3 and node 2. So, it will be B3 B2, okay. B3 B2, okay. And let us do the scatter operation here itself. So, scatter operation will be W1 W2 W3, and then the coefficients we will write it as 0 0 1, and second one will be second column will be 0 1 0, and we can write this we can multiply these two terms these two matrices, and we will get B3 L1 by 3 plus B2 L1 by 6, and here B3 L1 by 6 plus B2 L1 by 3. So, we can multiply it or keep it as it is. So, this is our scatter operation, and now what we will do is we will multiply these two terms and see what will happen. Okay. So, we will get this is a 3 by 2 matrix, 3 rows 2 columns, and this is a 2 rows 1 column. So, you will get a 3 by 1 matrix. So, you will get a force vector like this. First term is contribution will be 0 at first node, second node contribution will be B3 L1 by 6 plus B2 L1 by 3, and third node contribution is B 3 L 1 by 3 plus B 2 L 1 by 6. Okay. So, this matrix is what we have called as the I think this matrix is LE FE omega. Okay. LE transpose. This matrix is L 1 transpose F 1 omega. Okay. So, we can repeat the same exercise for the second element. So, if E is 2, what will happen? So, this integral we will write it as, now we are operating between node 2 and node 1. So, we will have W 2 W 1 and then the vector L 2 by 3, L 2 by 6, L 2 by 6, L 2 by 3. So, what I am doing here is I am doing this operation now for element 2, W 2 of x, B 2 of x dx, okay, between x 2 1 to x 2 2. So, on the right hand side we have B 2 and B 1. So, that will be there B 2 and B 1. This is for element 2. Again we can do a scatter operation now. So, if you do a scatter operation, it will become W 1, W 2, W 3, and then we will put the for the first column only W 2 has coefficient 1 and remaining are 0, and for the second column only W 1 has coefficient and remaining are 0. And then this matrix we can write as B 2 L 2 by 3 plus B 1 L 2 by 6 and B 2 L 2 by 6 plus B 1 L 2 by 3. And then this entire thing we can write in a matrix form as so, this is this will this we can denote it by this will denote it by dW transpose. Okay. So, I will write dW transpose here, and then this 2 we can multiply and we get a 3 by 1 matrix. So, the first term is B 2 L 2 by 6 plus B 1 L 2 by 3, and second term is B 2 L 2 by 3 plus B 1 L 2 by 6, and third term is 0. Okay. So, if you sum up this, so this term is you can call it it is the L 2 times F 2 omega. Okay. So, we can sum up these two terms and we get the second integral as integral 0 to L W B dx. It will be the summation of dW transpose, we can take it out, and then it will be summation of L 1 transpose F 1 omega plus L 2 transpose F 2 omega, and I think there is one term for it. We can, I think we can call it as F global F omega. Okay, we will call it as F global. Okay, just write F global body force vector. Okay. So, again we have taken this dW term outside, and then we have our body force vector. Okay. So, the second term is also done. So, in our evaluation, first term we have calculated in earlier class, and today's class we continued with that, and then we have the body force term. Now, let us look at the third term, WA T bar at x is equal to 0. So, at x is equal to 0, we have a traction boundary condition. So, if you write a, it will be again a force vector with three rows, and contribution will be at the third node only, and at node 2 and node 1 it should be 0, okay, because traction is acting at node 3. So, the contribution will be only at the third node. So, let us do that calculation W A T bar at x is equal to 0 using our shape function matrices. So, what we will do? We can write it as, so what is W? W is the weighing function which we denote it as in terms of element summation we can write, I think summation. Let us write it in terms of element summation. Sigma E is equal to 1 to number of elements, and then we have W E A T bar at x is equal to 0. Okay. So, A again will be A E, because we are at that in that particular element. Now, what we can do is, again same exercise we will do. W is actually W1 E, W2 E, and then N1 E of x and 2 E of x. And we have A E times T bar at x is equal to 0. Okay. So, we can have a scatter operation for this problem. So, this matrix will be W1 E, sorry, if we do a scatter operation, we will have dW times dW transpose times LE and then our summation E is equal to 1 to number of elements. Okay, so, I am doing the scatter operation here. So, we can take out dW term outside, and interior part we have the summation. So, what we will do is, we will call this this part as, we will denote it by Fe tau, okay. And it is the terminology used is, it is the element boundary force matrix. matrix. Okay. So, it looks very abstract. So, if you let us do the implement it for this 2 node element and see what we get. It is easy. If you let us take for element 1 e is equal to 1, what happens? So, for element 1 node 3 corresponds to x is equal to 0 and 2 and 1 it has different values, 1 corresponds to x is equal to L. Okay. So, for element 1 we are working with node 3 and node 2, okay. We are working with node 3 and node 2 global nodes. So, f1 of tau will be n3, okay, it will be n3 of x. So, ne3 of x and n2 of x times a1 times t bar, and this is evaluated x is equal to 0. So, what will happen is at x is equal to 0, n3 of 0 will be 1 and n2 of 0 will be 0, because the shape functions are such that n3 of x will have 1 here value and 0 at 2. This is n3 of x, and for shape function 2 it will have value of 1 and 0 at the remaining place. So, this is n2 of x. So, effectively what will happen is we will get 1 comma 0 and then our a1 of t bar. Okay. And if you multiply with the what happens to the second vector at element 2, if you look at element 2, what will happen? Element 2 you are working with node 2 and node 1. So, you will get f2. So, you are working with f2 tau. So, here we will be working with n2 of x, actually it is n2 actually n2 of x and n1 of x, and then we have our a2 term t bar at x is equal to 0. So, this term and this term are not x is equal to 0. So, this is x is equal to L and node 2 it is x is equal to some intermediate point which is not 0. So, effectively what will happen is this matrix will be 0 and 0, because the shape functions only at node 2 is if you evaluate the shape function is like this and where it is not equal to 0. So, we will get 0 and 0. Okay. So, x is 0 is here. So, at remaining whatever shape function we have, those will disappear, because our x is 0 is outside that element. Okay. So, if the value we are evaluating is outside the element, so the shape function values will go to 0. Okay. So, effectively we can multiply this L1 transpose F1 tau plus L2 transpose F2 tau, and then we can take the dW term out. So, this is what we will have. So, dW transpose will be out, and L1 and L2 we have already evaluated in earlier slides. Okay. This is L1, I think this is L1 transpose, and this is L2 transpose. Okay. So, we can just plug in there and see what will happen. L1 transpose is 0 0 0 1 1 0 0 0 0 1 1 0, and F1 is 1 0 times A1 t bar, and L2 tau we do not need it, we will just write it like this because F2 term is 0 0. Okay. So, effectively we are getting dW transpose, first term is 0, second term is also 0, and third term is 1, A1 T bar. So, what is happening here? We are seeing that the contribution of the element boundary force matrix is coming only at the third node. Okay. See here, it is the contribution is happening at third node, node 3. And you see here same thing, because why? Because the traction is applied at node 3, at remaining node 1 and node 2 there is no traction. So, the contribution in the force vector, global force vector. Okay. So, we can call this matrix as global boundary force matrix. So, the contribution is coming only on the third node. Okay. So, we have evaluated all the 3 terms of this weak form. Okay. We have substituted the trial solution and the weighing function in the weak form, and then evaluated the evaluated each term. Okay. So, to summarize, let us summarize this. So, we can summarize this. Effectively what you are getting, the first term we are getting as dW transpose K global times U global. Okay. And then the second term we will get a summation of these 2 terms. So, you will get F global vector, which is a 3 by 1 matrix multiplied by dW transpose. And fourth term we are getting a, let us call this as F tau global boundary force matrix. So, I am summarizing all these 3 things now. So, effectively the weak form boils down to dW transpose, we take it out, and then we are left with K global, U global minus F body force matrix, global body force matrix minus F traction F boundary force matrix. Okay. This term is 0. These values are arbitrary. Okay. This equation is valid for any W of x. So, this is arbitrary. So, the only way this equation will be satisfied is if this term goes to 0. Okay. So, let us summarize. If you look for the 3 node element, what will happen is you will get a matrix like this. Okay. You will get a matrix, K global will be K11, I am writing it K11, K12 just for simplification. I will not write the actual values here. It is a symmetric matrix. And then we have our U1 bar, U2, U3, this is the global force matrix, and that is equal to F omega plus F tau. So, what I had was a body force matrix plus a traction force, traction boundary condition. Okay. So, I had a traction boundary condition A1 T bar. Okay. So, this was A1 T bar, and here we had a body force terms. I'll write as, maybe I'll write it as F1, F2, F3. Okay, I'll just write it as F1. I cannot write it to body force terms. I think I will. And there was one more term which was the reaction term. So, R1 0 0. Okay. So, this is the first reaction occurring at node 1, okay, because we are prescribing the boundary condition, essential boundary condition, there will be some reaction. Okay. I think with this information we can go ahead and solve for the unknown values. How will you do this? In this problem, this is known, this is known, this is unknown. Okay, this is let's change it. So, in this problem U1 bar is known, unknowns are, I will mark him with red, U2 is unknown, U3 is unknown, and R1 is also unknown. Okay. So, what I can do is I will split the matrix like this. Okay. And then I will work with this matrix and this matrix, the first two row, last two, second and third row I will work with that. Okay. So, if I work with the second row and third row, I will get like this K22, K23, T bar. So, you can solve for U2 and U3. Once you do that, then you can calculate, I think I made a small error here, there will be one missing terms here, which is K21 U1 bar and K31 U1 bar. Okay. Okay. Now, we can solve for U2 and U3. After solve for U2 and U3, we can calculate R1. R1 will be K11, K12, K13 times U1 bar, U2, U3 minus F1, F2, sorry, minus F1, okay, minus F1. Okay. So, we can find the U R1 also. Okay. So, in this class we have substituted the trial solutions and the weighing function in the weak form, and then we have obtained the finite element formulation, which is this one. Okay. This is the FEM equations. Okay. Okay. And for this specific problem, we have these matrices, stiffness matrices, force, global force vector, traction boundary force vector, and then the reaction. Okay. So, thank you for your attention, and we will meet again on Thursday. Thank you.